you have a truss, and this truss is under the effect of dead load, live load, wind load, snow load. We are expecting snow in Commerce this week, probably. So after the structure analysis, we have two cases, no other. The first one, your member is in tension, or the member in the truss in compression. No third choice, because all of the members of the truss must be under the effect of axial load, tension or compression. We learned last week how to design tension member. This week, we need to understand, we need to learn how to design compression member. Next meeting on Thursday and Tuesday next week, we will start to design this connection. Okay, so today the meeting is about designing compression members. Compression member are structure elements that are subjected only to axial compression, like columns, trusses, bracing system. We can find compression member everywhere. But in this course, in this part of the course, we are talking about compression members in truss. Okay? If the axial load B is slowly applied, it will ultimately become large enough to cause the member to become unstable. The member is said to have buckled, and the corresponding load is called the critical buckling load. We have a very important phenomenon for member under the effect of compression or compressive load. This phenomena does not exist if this member under the effect of tension. If you have a member under the effect of compression, we can expect something called buckling. This phenomena does not exist if the member under the effect of tension. This only happened if the member under the effect of compression, and it's a big issue. So we have something called B critical, which is called critical buckling load. Guys, make sure you are understanding this concept. Please pay attention. We have two situations. P ultimate greater than phi Pn. Phi Pn from the design philosophy is the design ultimate strength of any member. If the applied load is greater than the design ultimate strength, your structure or your member is unsafe. For member under the effect of compression, we have P ultimate is greater than P critical. That means this member can be called unstable. There is a big difference between unsafe and unstable. We have a difference between unsafe and unstable. Instability of structure means there is something wrong with this structure. Suddenly, this structure will collapse because it's unstable. So, if you have a member under the effect of compression load, we need to check instability of this member by making sure that the applied load is smaller than the critical buckling load. Because if the applied load greater than the buckling load, that means this member is unstable, not unsafe, it's unstable. Okay? Just to remind you, I believe this part of the course or the topic is covered somewhere. We have Euler, the column theory, saying P critical equal pi square EI divide KL, all of them square. Just keep in your mind. E Young's modulus of steel, it will not be given. You have to remember this number. E equal 29,000 KSI or 29 million PSI. Please keep this number in your mind. E for steel, Young's modulus of the material, Young's modulus of steel, because we are here in steel structure course. E Young's modulus 29,000 KSI or 29 million PSI. I moment of inertia of the cross section, IX or IY, which one is the minimum value? Because we are looking for the weak direction. So we have two values. If you open any table, section properties, you can find IX and IY. Moment of inertia about x-axis, moment of inertia about y-axis. Which one I'm gonna use? For buckling, I'm gonna use the minimum value. L, the total length of the member. L is the total length. Sometimes this member is supported here by hinge, sometimes by fixed, sometimes it's free. So we have something called K, which is the effective length factor. K equal 1 if the member is hinge, or sometimes called pin. If the member is fixed from one side and free from the other side, the value of K equal 2. K equal 0.5 if the column or the member is fixed. If the member is fixed, hinge or pin, K equal 0.7. For truss members, we are in this scenario. For truss members, all truss members are pin connections. So K equal 1. So if you multiply K, which is 1 times L, the member length, I can figure out the denominator for this equation. So P critical for any member in the truss equal pi square E I divide KL, all of them square. That makes sense? This equation can be converted to a different way as a function of area and R. R can be called the radius of gyration. It's a section properties function of I. So we have Rx and we have Ry. Which one is the smallest value? Keep in your mind, we have a term here called L, the length of the member, divide R, the radius of gyration, is called the slenderness ratio. Slenderness ratio is indication if the member is more critical to buckling or less critical. Okay? So sometimes we can expect a problem, especially in the homework, to calculate the P critical. the value of Ix from the table, or Iy, I'm gonna use the smallest value. If you are looking for radius of gyration, we have two values. If you open the table, Rx and Ry, I'm gonna use the smallest one. If you divide L by R, the smallest value of Rx and Ry, you can find something called cylinder rest ratio, if it's required. And this slide showing you what are the different scenarios. If the column or the member is different, has a different connection at the two ends, hinged, fixed free. Cooley, what are you doing?
My signal's really bad, so it keeps kicking me out, and then when I log back in, it makes my mic come back on.
Okay, got you. Thank you. So the member can be hinged, fixed free, fixed, hinged. Okay, based on these conditions, I'm gonna figure out the value of K. Besides the value of K and L, I can figure out the denominator. Using pi square EI, I can figure out the value of P critical. Let's do this example. It's a very interesting example. We have a column with cross-section W 12 times 50. Guys, you are right now has a more experience with the steel structure, so you can understand what is the meaning of W 12 times 50. W means we have W shape cross-section. This W shape looks like this. That makes sense? W shape 12 times 50. So I can open the tables. We have here tables of steel structure. What is the name? One more time. 12 times 50. So if you go back, if you go down, I'm sorry, 12 times 50. Go down more. 12 times 50. Here you go. This one. W 12 times 50. From this table, I can figure out the total the dimensions of the cross section, like what is the depth, what is the thickness of the web, what is the thickness of the flange, width of the flange, and also what is the value of Ix, what is the value of Rx, what is the value of Iy, what is the value of Ry. As I told you, we have Ix and we have Iy. We have R small x, which is radius of gyration. We have R small y. Okay? So keep in your mind, if any cross section is given, you can open the table of steel cross section and make sure you are on the right shape. We are here W 12 times 50. So please open the tables for W shape. And then figure out where is the number of this cross section 12 times 50. This page will give you the different dimensions, like depth, like thickness, like width of the flange, all of this stuff. And the second page will give you the section properties about x-axis and about y-axis. This is how you can use the table of cross sections. So final conclusion, Ix equals 391 inch to power 4. Iy equal 56.3. Which value I'm gonna use for buckling or for P critical? I'm gonna use the smallest value. So I equal the minimum value of Ix and Iy, which is 56.3 inch to power 4. This member has a length equal 20 feet. So L equal 20 feet. The top end is bent and the bottom end is fixed. So this column is fixed at the bottom, bend at the top. Can you tell me what is the value of K? You can go back here. If you have a column with fixed from one end and hinge or bend from the other end, K equal 0.7. So K equal 0.7. And given E for steel, 29,000 KSI. Can you tell me what is the critical buckling load? Yes, I can. It's a very simple step. B critical equal pi square E I divide K L, all of them square. Put your numbers. Pi square E 29,000 I, the smallest I, 56.3, K 0.7, L 20, all of them square. We have a little mistake here. If you get a number, your number will be wrong because we have a little mistake. Please review your units. 29,000 is KSI. So we have kib and inch square. 56.3 is inch to power 4. Until this moment, we are good. K is a factor. We don't have unit. L in feet. We have a little mistake here because you have in the numerator inch. In the denominator, we have feet. So you have to convert this length to inch. I'm going to multiply it by 12. This length equal 20 feet. Please multiply 20 by 12 to convert it to inch. So your final value will be pi square times 29,000 times 56.3 divide 0.7 times 20 times 12, all of them square. Your final answer will be 570.9 kip. We need to make sure that any force in this column must be smaller than or equal this value of critical buckling load to make sure this column is stable. That makes sense? So the problem is asked for what is the critical buckling load. Okay. So we learned from this example how we can use the table of steel cross sections to figure out the section properties and then how we can set up the critical buckling load equation. Guys, I have a technical issue here, so I will restart my laptop. Just a second, okay? Don't go away. So guys, I'm back. I'm so sorry. So guys, do you have any question so far? Do you have any question so far how to calculate the buckling, the critical buckling load for a column? Okay, this is to check the stability of the member under compression. If you would like to design the member, Pn, the nominal design strength, equal F critical time area gross. This is the only design equation. By the way, we learned before, if you would like to convert this nominal design strength to design a compressive strength, you need to multiply it by phi. The value of phi for compression member is 0.9. So phi Pn equal 0.9 times Pn. I have question. I have a question. If you have a member like this, or plate like this, and we have a hole here, and we have tension, the same member under compression, and we have hole, we understand that this hole will have a bolt. Going to the other side. We understand that we have bolt going to the other side. If you have issue at this location, what is the area of the member? It will be area net. Why? Because the location of the hole does not work. The only working part of the member is this part and this part. But if this member under the effect of compression, I believe the hole which is filled with the bolt material can work with the member. So we don't have area net if this member under the effect of compression. We have area gross. You will say, hey, we have hole. Yeah, I understand, but this hole is filled with a bolt. And this compression load can be supported with this filled bolt. So we have only one scenario using area gross. We don't have area net or area effective in the case of member under compression. How can I figure out the F critical? F critical is called the critical stress. We have two scenarios. We can calculate F critical from this expression, or we can calculate F critical from this expression. Which one I'm gonna use? Based on the relationship between KL over R and this expression. If it's smaller than or equal or greater than this expression. Just to give you a hint, we understand what is the meaning of K. Just to remind you, K depends on the end conditions of the member. For your information, for any truss member, we have this scenario, K equal 1. L is the length of the member. R we have two value of r. R is the radius of gyration. We have rx and we have ry. I'm gonna use the smallest value based on the values in the table. 4.71 square root E Young's modulus of steel 29,000 KSI. If yielding stress of the steel based on the type of the steel, so I can determine this condition or this condition. For example, if you are talking about the first condition or the first case, F critical equal 0.658 to power F yield design FE, all of them time F yield. Okay, we understand what is the meaning of F yield. We understand what is the meaning of F yield. What is the meaning of FE? FE is the buckling, critical buckling stress, which equal FB critical divide area. Do you remember the critical buckling load that you calculated before? Please divide this number by area. You can get the critical buckling, the critical buckling stress. Okay? If the second condition is exist, F critical equal 0.877 FE. FE is the critical buckling stress. Let's do an example. The compression member is very easy. We have two angle 6 by 6 by 1/2 of steel A36, has a length of 20 feet, and the bend ends computes the design ultimate compressive strength. Okay, we understand we are looking for design ultimate compressive. So phi Pn, why phi? Because we are looking for design, not nominal, equal 0.9 F critical area gross. That makes sense? That makes sense? What is the value of area gross? What is the value of R small x? What is the value of R small y? What is the value of L? What is the value of K? All of this information we need to answer. Okay, I'm gonna open my table one more time. The angles is double angle 6 by 6 by 1/2. Okay. Do you have members here double angles? I believe yes, we have. Do you remember that? This is one angle. I believe we have double angle. No? No, if you go down. Yes, here you go. We have double angles. We have tables for double angles. One more time, the cross section in this problem is 6 by 6 by 1/2. So 6 by 6, there you go. 6 by 6 by 1/2, this one. 2 angle 6 by 6 by 1/2. This table can give you we will go to the other page. 6 by 6 by 1/2 can give you what is the value of radius of gyration, which is Ry. If you go back to the previous one, okay, we can use this one. Ry is the smallest value. So I'm gonna assume any separation of this value in 1. let's do 38. So the value of radius of gyration R will be 2.63. Okay? This one will give you 2.63. Guys, to give you a hint, this double angle looks like this. We have a space between this side and this side, which called back to back distance. This distance can be three values: 0, 3/8, or 3/4. Inch, inch, inch. We are not using 0 because we expect something to fill this gap. So we can assume this distance or this distance is up to you. It's not a big deal, okay? So I'm gonna use 2.63. The difference between this value and this value is nothing, just a little bit. So I'm gonna use the middle one, 2.63, which is radius of gyration about YY, which is the smallest value. What is the area gross? I forget. The area gross is 11.5. Area for the double angle, 6 by 6 by 1/2, 11.5 inch square. This one is inch. What is the length of this member? Is given 20 feet. Please convert it to inch. So I'm gonna multiply it by 12. It will be 240 inch. What is the value of K? Because it's been ended. So will be 1. Okay. So what is the value of K? L divide R. K is 1. L 240 divide R 2.63. The value will be 91.25. Okay. What is the value of this expression? 4.71 square root E divide F yield. 4.71 square root E divide F yield equal 4.71 square root. The value of E, 29,000. The value of F yield, because you have steel A, 36. F yield equal 36 KSI. Can you give me the value? 29,000 divide 36 square root times 4.71, 133.68. So the final conclusion, KL divide R, which is 91, is smaller than 4.71 square root E divide F yield, which is 133. So you are,
Okay.
yes.
Isn't 29,000 is KSI, and then you're dividing by 36, or sorry, PSI and dividing by 36 KSI?
No, this one is KSI. This one is KSI. 29,000 KSI, 29 million PSI.
Okay. Thank you.
Yeah. If you go back, I gave you this information here. E for steel, 29,000 KSI or 29 million PSI. Okay, so right now, KL divide R is smaller than 4.71 square root E divide F yield. So we are in this scenario. F critical equal this value 0.658 to power F yield divide FE, all of them time F yield. Everything with you except FE. FE equal P critical divide area. The value of P critical pi square EI divide KL square. This is the value of P critical. Divide area. That makes sense? Go ahead and put your number. Pi square E 29,000. I go back. What is the value of I? We don't have a value here, but we can get it. We need to go back to the single angle. 6 by 6 by 1/2. This one. What is the value of I? X. $19.9. This is for one angle. So the two angles will be 39 by 0.8. So the value of IX 39.8. IY for one angle 19.9, the same value for one angle. So for two angle, I will multiply it by 2, 39.8. That makes sense because they are equal to equal legs. I'm gonna use the smallest value, which is 39.8, which is the value of IY or IX, whatever. K is 1, L 240, all of them square. Divide area, the area of the two angles 11.5. So guys, what I did, just to give you a hint, I went to the table for double angle. I didn't find IX or IY. So what I did, I go back to the table for one angle and I get the value of IX and IY for one angle. Just multiply them by 2, you can get the IX and IY for double angle. It's very simple. Okay? So what is the value here? Pi square times 29,000 times 39.8 divide 240 square divide 11.5. This value is 17.19 KSI. So if you put this number, 17.19, if yield is 36, if yield is 36, I can give you the value of F critical. This value will be 14.99 KSI. If you can find the value of F critical, go back here, put F critical equal 14.99, the value of area gross 11.5. Then finally you can get the design compressive strength 0.9 times 14.99 times area gross. Your final answer will be 155.1 kip. Very simple. Very simple. Just you have a cross section and I can tell you what is the design compressive strength of this member. Please make sure after you are done with this calculation that the P ultimate from RISA analysis or from structure analysis is smaller than or equal the design normal strength, the design compressive strength of the member to make sure this member is safe against the applied load. One more example. One more example. We have a compression member is subjected to surface load. We have 105 dead load and we have 150 live load. Okay, from this information, from structure analysis, I can say P ultimate equal 1.2 dead load plus 1.6 live load. So your final answer will be 1.2 times 105 plus 1.6 times 150. Your value will be 366 kip. The length of this member, 18 feet. I'm gonna convert it to inch, step by step. 216 inch. And is bend at each end. So K equal 1. And the steel, area steel is A36. So F yield is 36 KSI. Can you select a double angle section? This example is actual design. Can you select double angle section? Yeah. We don't have guide. You need to assume, and based on your assumption, you can design. We need to assume something. What do you think? Assume. Okay, let me say something. This one was 6 by 6 by 1/2, give you a strength 155. We are looking for something here 366. No, we need to go bigger. So I'm gonna assume double angle 8 by 8 by 1/2. And let's see. What is the area? What is the value of R? What is the value of I capital X and I capital Y? Both of them should be the same value. Okay, so guys, I assumed a member. We don't have guide to give you a hint. So we need to assume, based on your assumption, I will do my calculation for design. 8 by 8 by 1/2. 8 by 8 by 1/2. I think we have in this member. But please make sure you are in the table for one angle. So the area for 8 by 8 by 1/2, this area for one angle. I'm sorry, this area for one angle. 7.84. 7.84. Because you are in a table for one angle. 7.84. I am going to multiply it by 2. So the value of area gross, 15.68 inches square. For some reason, if you go down to the double angle, okay, you can use the value as it is. 8 by 8 by 1/2, the value of the area is 15.7, like I did. 15.68 looks like 15.7. That makes sense? So please make sure which table you are using. If you are using tables for double angle, okay, use your number as it is. If you are using a table for one angle, please multiply it by 2 if you are talking about double angle member. Okay, let's do it here. What is the value of R, radius of gyration? I'm gonna use this one, 3.43. What is the value of I capital moment of inertia IY or IX? Unfortunately, we don't have these values here. So I will go back to the tables for single angle. Eight by 8 by 1/2. So 8 by 8 by 1/2, we have here 48.8 for IY. And we have here IY 48.8. Both of them the same. 48.8. That's right. Yes. Okay. We are good. Keep walking. Phi PN equal 0.9 F critical area gross. To figure out the area F critical, we need to figure out KL divide R. K is 1, L 216 divide R 3.43, 62.9. Okay, we need to figure out the value of 4.71 square root E divide F yield. I believe this value will give you 133. So KL divide R is smaller than 4.71 square root E divide F yield. So the value of F critical equal 0.658 to power F yield divide F critical, all of them time F yield. We understand that everything is given. F yield 0.658. We're still looking for FE. Okay. The value of FE for this example equal pi square EI divide LKL, all of them square, divide area. Put your numbers. That's it. Pi square E 29,000. I for this member that you assumed equal 48.8. K is 1, L 216, all of them square, divide area of this cross section that you assumed 15.68. So the final value for FE will be 19.1 KSI. Okay, put the number here. This one 19.1. This one is 36. This one is 36. So I can figure out the value of F critical. .35 KSI. Put the value of F critical 16.35. Area gross equal 15.68. So I can figure out the value of design compressive strength. It will be 230.75. Wow. It's unsafe. B, ultimate still greater than phi Pn. It's unsafe. We need to increase the member to use a bigger one. Okay, if you open the table, do you think we have a bigger? This is the biggest one, 8 by 8 by 1/2. Probably you can use this one with a greater thickness, but I believe it will not work probably. Anyway, you need to increase the cross section. One of you will say, hey, if I tried the biggest one, L angle 8 by 8 by 1 inch and 1/8, and doesn't work, what should I do? We don't have any bigger cross section. What should I do? Please change the cross section. Angles will not work. You cannot use channel, or I highly recommend for biggest bridges or structure to use the W shape. So this is a good question. One of you will ask me, hey, Dr. Ayman, if I selected a cross section and I tried to do my design, and finally the P ultimate is still greater than the design compressive strength, what should I do? You have to increase the cross section. Okay, I increased it to the maximum. We don't have any bigger cross section in the table. And it's still unsafe. What should I do? You need to change the shape of the cross section. Instead of double angle, you have to use a different shape, like W shape or a channel or any other cross section.